Okay, in this video we're going to look at some applications of Newton's second law. And here's the first example. So we've got two forces, a 90 Newton force and a 100 Newton force acting on a 1 kilogram object as shown, and we want to find the acceleration of the block. So what's our strategy going to be? Our strategy is going to be to find the net force and then apply Newton's second law. So we know that the acceleration is equal to the net force divided by the mass. And so we want to find the acceleration. We've got a mass, we've got some forces. All we have to do is find the net force and Bob's your uncle. Now, acceleration is a vector, force is a vector, and so we are going to do the vector sum of these two forces here and here. So we know that if we look at the picture here, we've got this x component, which is 100 newtons. The y component is 90 newtons. The net force, these are connected tail to tail. So if I think of this as parallelogram vector addition, the net force is going to be along the diagonal of the parallelogram. I could have also done tail to tip twice if I wanted. But this net force is going to be at some angle theta. And we can find the magnitude of the force simply by adding them up, and so that's going to be 100 newtons in the x-hat direction plus 90 newtons in the y-hat direction. To find the acceleration, we simply divide that net force by the mass, and of course in this case it's 1 kilogram. Now we have newtons up above, we have kilograms down below. If we divide newtons by kilograms, we get meters per second squared, and so the acceleration is going to be 100 in the x-hat direction plus 90 in the y-hat direction. And you can see I've factored out the meters per second squared, so that's going to be the units of our acceleration. And then to find the magnitude of A, we simply use the Pythagorean theorem, 100 squared plus 90 squared, then take the square root. And that gives us 130 meters per second squared. And that, if you want to put it in scientific notation, would be 1.3 times 10 squared. But that really just means 130. And then, of course, theta is going to be the arctangent of the y value, the opposite value, over the adjacent value, which is the x value. So that's 90 over 100. Technically 90 newtons divided by 100 newtons, but guess what? The units cancel. So it's just 90 over 100, take the arctangent. And so we get the acceleration is 1.3 times 10 squared meters per second squared at a 42-degree angle. And that's how you get the answer to the problem. Here is another simple example. Determine the force of gravity acting on some object of mass m. Now, we know that the sum of the forces is equal to ma. But what's a for gravity? The acceleration for gravity is little g pointing downward. And so the sum of the forces is just going to be the mass times the acceleration due to gravity, which is g, or 9.8 meters per second squared, in the negative y-hat direction. Or simply we could say mg pointing down. And so mg is the force of gravity acting on the object. And what do we call the force of gravity? That's the weight. So anytime you need to know the weight of something, it's simply going to be mass times little g. Now, just a few things to note. The weight of an object can be determined by multiplying its mass times acceleration due to gravity. Now, weight is a force. We always want to remember that. Weight is a force. And so that means it typically has units of newtons. Sometimes it might be pounds, but in the metric system we tend to use newtons. And one of the things we want to remember, the weight, we have W is equal to m times little g. The mass and the weight, those guys are related, but they're different. And so one of the things that can highlight this, if you were to travel to the moon, your mass would be the same. I mean, think of what your mass is. It's how much matter is in your body. It's the measure of the inertia of the matter in your body. So if you go to the moon, unless someone chops your arm off or something, you're going to have the same amount of mass as you have on the Earth. But if you go to the moon because the force of gravity is weaker on the moon than it is on the Earth, your weight on the moon would be less than your weight on the Earth. Just be aware now, there is a distinction between the weight and the mass of an object. The mass is an intrinsic property of the object and it stays the same, but the weight, that's the force of gravity. The next example we want to talk about is calculating the so-called normal force. Now that's a weird name, normal force. The reason they call it the normal force, as we'll see in a sec, is it's always going to be normal, or that's a fancy mathematical term for perpendicular. It's always going to be perpendicular to a surface. And so they call it the normal force because it's the perpendicular force. Now here's the idea. I've got my block, it's sitting on a table. We know the weight of the block is going to be m times little g, but that table is going to be pushing back. How do we know that? Because the block is not accelerating downward. There must be another force balancing it. We also know that if gravity pushes this block into the table is going to push back with an equal and opposite force, according to Newton's third law. So the force of the normal force is going to be equal to the weight in this case. Now, we can argue that with using Newton's third law, but we can actually see it with Newton's second law. Let's consider my picture. Now, I have drawn my picture, and I've drawn all my force vectors on the picture, and I've set up a coordinate system. Remember, the coordinate system is designed to show you the directions of things. So any force pointing to the right is positive. Any force pointing to the left in the negative x direction would be negative. Now, all of these forces are in the y direction, so there are no x forces to worry about in this example. But along the y direction, anything pointing up is going to be positive because that's how I define positive with my coordinate system. Anything pointing down, you guessed it, it's going to be negative. So the normal force is going to be in the positive direction, and the weight, or m times little g, is going to be in the negative direction. So if I want to apply Newton's second law, I'm going to do the sum of the forces is equal to m times a. And so here I've got the sum of the forces. It's going to be positive Fn, because that's in the positive direction, minus mg. Mg is pointing down, that's why it's minus. That's equal to m times the acceleration. Now, the acceleration is going to be 0 in this case. Why is it 0? How do I know that? Because this block is not leaping off the table in the y direction. It's not crashing through the table in the y direction. It's just sitting there. It's got no acceleration at all, so the acceleration has to be 0. So that means that the normal force minus mg equals to 0. And so I can solve for mg simply by moving it over to the other side. It becomes positive over there, and I'm left with the normal force is equal to the weight. Now, let me give you a caution. Very often that's true. The normal force works out to be the weight. But we're going to see later on, there are many examples where the normal force is not the weight. It might be the weight times something, it might be the weight plus something, it might not be related to the weight at all. So you have to find the normal force in every one of these problems that has a normal force. You have to figure out what it is. How do you find the normal force? Well, I just showed you. You do the sum of the forces, set it equal to ma, and then you solve for it. That's all there is to it. That's how you find the normal force. Now, I just mentioned that the normal force is not always equal to the weight. Here's an example where it's not equal to the weight. I have my block, again, sitting on the table, but there is an additional force, which I've labeled as F, pushing down on the block. And so what do? I want to figure out what the normal force is. How do I find it? I do the sum of the forces. I set them equal to ma. Now my acceleration is again equal to 0. So when I apply the sum of the forces, and this is in the y direction because there are no x forces, I get the normal force, which is positive because it's pointing up. I get minus mg and minus f. These are forces on my picture. They're minus because they're pointing down. And so Fn minus mg minus f is equal to 0. Again, what do I want to do? I want to solve for that normal force. And so I'm going to solve for the normal force. I'm going to bring that one over and that one over, and I end up with the normal force equal to the weight plus the force of pushing. And so that is something I hope makes sense, that if the block is just sitting there, the normal force is going to be equal to the weight. But if I come later and I start pushing down on it, the table has to push back up to match both the weight and the force I'm pushing down with. That's what the math tells us. And so the normal force in this case is not just the weight, it's the weight plus the pushing force. Now here's another example, it's very similar, but instead of the pushing force pushing down, it's turned into a pulling force that's pulling up. Everything else is the same, except whereas before this was in the negative direction, now it's in the positive direction. I've got two positive forces and one negative force. They're all in the y direction, so when I do my sum of the forces, I get the normal force, positive, minus the weight, plus the F, because it's pointing up. That's equal to ma, but a is 0. Again, not leaping off the table. So when I solve for the normal force, just doing the algebra, I get it's equal to mg minus the force. And hopefully that makes sense too. If this guy is pulling this block up, not enough to lift it off the table, but enough to counteract some of the weight, the normal force is going to go down because the block is being pulled up and not the table is not going to feel the full weight of the block. And so what will it feel? What's it going to have to push back with the normal force? The weight minus the force with which it's being pulled up. I think that result's probably pretty intuitive. You probably would have guessed that, but we see the math makes it explicitly clear. And the reason why I'm going through these simple examples is I want you to see these patterns. What are we doing in all of these problems? We're drawing a picture, we're labeling our forces with our force vector arrows, we're setting up a coordinate system, we're going to break all of our forces into x and y components. So far they've all been along the y direction or the x direction, but we're going to have angles pretty soon. What do you do with it? You just say all the forces in the x direction and all the forces in the y direction, you add them up, you set them equal to ma. That's all you do. Now here's a force diagram that has more forces, and what we have here is a block that's sitting in the corner of a room, and we have the weight is pushing down on the block. We have the normal force, and I've labeled this as the normal force of the floor, so that's the Fn for normal force, and then there's an F right there for floor. And I've got this just F, which is a pushing force, but now it's pushing at a downward angle of 30 degrees. So it's a 100 Newton force pushing down at 30 degrees. And so it's also being pushed into the wall over here, so the wall is going to exert a normal force. FNW, W is for wall. And what we want to do in this problem, it says determine the two normal forces, the floor normal force and the wall normal force. So how do we do that? We're going to break all of our forces into x and y components. We're going to sum the forces along the x, sum the forces along the y, and do some algebra. Now I'm going to show you a technique for handling more complicated pictures like this. So this has got a lot of forces on it. It's a pretty complicated picture. It can be a little confusing. So what I've drawn here over on the right is something that's called a free body diagram. This can be a very useful tool for analyzing problems with lots of vectors on them. Basically what you do is you set up your XY coordinate system and you move all your forces over and you connect them all with the tail of every force at the origin. So here's my normal force with the floor. I've set it to the origin so it points up. The normal force with the wall, I've moved it over so that its tail starts at the origin and it's to the left. This downward force here, this 30-degree downward angle force F, I've got it set drawing from the origin, moving at a downward angle theta. And then I've got the weight, which is pointing straight down. Here's the weight. I just move it right here. And those are all the forces on my picture. Now I can break all the forces into x and y components very easily and see which force is which. Now, the normal forces are already along the axes. The weight is already along the y-axis. This F force is the only one at an angle, so that's the only one I have to break into pieces. And so I break that into an x component, which is going to be F cosine of theta. I break it into a y component, which is going to be F sine of theta. and now I have every force pointing either along the x direction or the y direction, positive or negative. Now, keep in mind, this is pointing in the negative direction, so this is a negative f sine of theta, but I can see that because my arrow is pointing down. So I've got my free body diagram here. Let's recap what we're given. We're told in the problem that the mass is 10 kilograms. If I multiply that by little g, I get 98.1 newtons. And what's that? That's actually the weight. So the weight is equal to 98.1 newtons. That's mg. And we also have this force F, which is 100 newtons at a downward angle of 30 degrees. So Fy is going to be 100 newtons times the sine of 30, and we can calculate that. It works out to be 50 newtons downward. We could say also minus 50 newtons, but we know that it's pointing down. We have our X force is 100 newtons times the cosine of 30. That's 86.6 newtons, and that one's pointing to the right. How do I know that? I see it in the picture. I see this one's pointing down, this one's pointing to the right. And so I'm aware of what those mean in terms of our SIGN signs. All right, so we want to do this first sum of the forces. We're going to have to do the sum of the forces in the x direction and the sum of the forces in the y direction. We're going to do the x direction first. And so how many of these forces are pointing in the x direction? Now, first of all, let's note this brown force. I've completely gotten rid of it by breaking it up into an x component and a y component. This is tail to tip twice, and so we can ignore this force now because we've already broken it into an x and y component. So we want to find all the forces that are parallel to the x-axis, and that's going to be my fx, or f cosine of theta, which is pointing in the positive direction, and my normal force with the wall, this fnw, that's pointing in the negative x direction. Those are the only two forces pointing in the x direction. So when I do my sum of the forces, I get my fx is equal to my fn wall, and that's equal to max, but this is pushed into a corner. It's not moving. My acceleration is 0. And we just calculated that this guy was equal to 86.6 newtons. So if I move this guy over here, I get that Fx is equal to the normal force of the wall, and that's going to be equal to 86.6 newtons. So the problem was to find the two normal forces. I have found the one with the wall, and it's 86.6 newtons. Now let's do the sum of the forces in the y direction. How many forces are pointing in the y direction? We have the normal force with the floor, we have the weight, and we have this Fy sine of theta, the F sine of theta for Fy. And so we can say that that's going to be the normal force with the floor, and that's in the positive direction, so that's going to be positive because it's pointing up. Then we have the weight and the Fy, which are negative, so that's going to be minus mg minus the F sine of theta, or minus the Fy, and that's equal to ma in the y direction. And of course, again, the acceleration is 0. And so we can solve for the normal force with the floor. Fn floor is equal to mg plus Fy. And that gives us a value when we plug in the numbers, which we calculated previously, add them up, and we get the normal force with the floor is equal to 148.1 newtons. And that is the normal force with the floor, and that is what the second part of the problem asked for. All right, let's look at another example. Here I've got two blocks, block 1 and block 2, and they are connected by a rope which is pulled taut and there's a 100 Newton force pulling on block number 2, and it's going to drag both of these blocks together. Each of these blocks have a mass of 10 kilograms, and the rope is what's called an ideal rope. So we're going to assume that the rope has negligible mass. We can ignore the mass of the rope in this problem, and that it doesn't stretch. That means that if block 2 moves over 5 meters, block 1 has to move over 5 meters because this rope doesn't stretch. For all intents and purposes, you can imagine this as like a steel bar connecting them. In fact, if it is a steel bar, this problem has worked exactly the same way. Now the problem says a 100 Newton force is applied along the x-axis, causing the two masses to accelerate. And we're going to assume that there's no friction in this system. We're going to learn how to handle friction later. The question asks, find the acceleration of the system and the two forces, F12 and F21. Now, the first thing we can note is this force is going to pull this guy to the right, but the forces in the y direction, for each block there's going to be a weight and a normal force. Those forces are not going to create any acceleration in the y direction at all. So all the motion is going to be along the x, and we can ignore the y direction for this problem. So how do we approach this kind of problem where there are two blocks like this? One way to do it is to isolate each block and consider the relevant forces on each block. So let's consider block number 1. Over here I've got block number 1. We've got the weight, that's m1 times g. And by the way, that subscript, super important. Be very, very careful how you label these things. You know, make sure that everything that's different gets a different label and that you're consistent in using it, because if you don't do that, you'll mix stuff up and you'll get confused. So be very, very anal retentive about labeling things. This is the normal force, and it's the normal force on block 1, so I'm calling it Fn1. And then we have F21 pulling it to the right. Now what's F21? That's the tension in the rope, which is pulling block 1 to the right. Now what about this 100 Newton force? Because it's also pulling to the right, but it's not acting on block 1. It's acting only on block 2. So block 2 gets this 100 Newton force, and then there's this rope which transmits a force to block 1, and that's F21. And this subscript here, F21, that means the force of block 2 on block 1. And there's going to be a Newton's third law reaction force, F12, that's the force of block 1 on block 2. And so F21, F12, those are the forces transmitted through the tension of the rope. And of course we know by Newton's third law, those guys are going to be equal and opposite. But here we have just the forces on block 1, and we know that in the y direction these forces are going to balance, so we can ignore that for now. And that means on block 1 the only relevant force is F2 on 1. Now let's do the same thing and consider block 2, the block on the right. Here we've got F1 on 2, that's again the tension in the rope, so the rope is pulling it back this way. We have the 100 Newton force pulling to the right. The rope, which is attached to a block over on the left, is pulling it back to the left. We have the weight and the normal force again, which are not relevant to this problem because they balance. Again, I have my subscripts here, M2, Fn2. We're not going to need Fn2 in this problem, but later on we will need the normal forces, and so again, these labels, very important. Now we can apply these. Now on block 1, we had just the single force, the tension in the rope, F21, pulling it to the right. And so when we do the sum of the forces for block 1, we get F21 is equal to M1A. Why M1? Because this is block number 1. Now on block number 2, we had two forces. We had the force that was pulling the blocks to the right, and we had the tension in the rope, which on block 2, this was F12, the force of block 1 on 2. And so obviously the F is positive, the F12 is negative. We can see how our positives is defined by our coordinate system. And so for mass 2, I do the sum of the forces in the x direction is F minus F12, and that one's going to be equal to M2A. But F12 is equal to F21, which is equal to M1A up here. F21 is M1A, but that's F12 as well. So these two guys are equal by Newton's third law, so I can substitute them in, and when I plug F21 equals to M1A into here for F12, I'm left with F minus M1A equals M2A. All right, so let me rewrite what I had before. I had F equals to M1A plus M2A. Now, the A is the same for each block. How do I know that? Because I don't allow the rope to stretch. That's one of the assumptions that we're making. The rope is an ideal rope. It's not allowed to stretch. So the A's are the same. I can factor out the A, and I'm left with the force is equal to M1 plus M2 times A. Now I can plug in the numbers. I can solve for A, and I get the acceleration is 5 meters per second squared. Now the problem asks to find the tension in the rope, the two forces F21 and F12, and so if I want to find F21, I can just isolate block 1, because that's the block that had F21 operating on it, and I can say the sum of the forces in the x direction is equal to the acceleration in the x direction. And so the sum of the forces in the x direction is F21, and this is M1A. And I should be more careful about my units. So what am I going to do? I'm going to write in an A sub x here, because that is acceleration in the x direction. And this is really the sum of the forces in the x direction, and that is equal to F21 equals to M1A x. I plug in the numbers, and I find that F21 is equal to 50 newtons, and of course from the picture I can see that it's pointing to the right. So that's a positive force, and it's pointing to the right. Now we know by Newton's third law that the magnitude has to be the same. So the F12 is the same magnitude as F21, and that's going to be 50 newtons, but obviously that's going to be 50 newtons to the left. And of course that's the tension on the other block over here, and that force is going to be pulling to the left. Now, I found F21, and then I said Newton's third law tells me F12. I could also plug into the Newton's second law to find F12. Let's see how to do that. If we look at block number 2, we can say that the sum of the forces in the x direction are going to be the F minus the F12. So here we have F minus F12. That's equal to M2A. And again, that should be in the x direction. And when we solve this for the value F12, we just basically bring this guy over there, bring that guy over there, and we get F12 is F minus M2A. So that F was given in the problem to be 100 newtons. We have the 10 kilograms. The 5 meters per second squared is the acceleration, which we found previously. I plug that in, and I get 50 newtons. And of course, obviously from the picture, that's pointing to the left.